going up again. Yeah, so anyway, it's 10 past now, so let's get started. Okay, so the last time we looked at a few examples involving implications, which again, if anyone missed it, it's on the video, so you guys can recap that if you need to. Now let's see what we look at today. We start with direct proofs of implications. And again, this example comes out every year. It's probably there again as well. In your, I don't know if you guys looked at the assignment yet. There's probably one like this there. I've seen it every year, and in the test as well. No, sorry, the test is learning at 1. In the exam, this will definitely be there. And it's always phrased in a very similar way. So this question here, I just recommend you guys to remember how to do this one. Example of how to prove an implication. And we do this usually by direct proof. So this is the instructions are written above here. Let's zoom in. So to prove an implication, again, a recap, implication is just an if-then statement. So to prove an implication which has this form, if P then Q, it's enough to assume that P is true and from it deduce Q. So we start by assuming that whatever P is must be true. And from that assumption, can we then show that Q must also be true? That's how we prove these things, right? So a bit abstract, maybe an example will help. So let's see, I haven't looked at this one yet, so hopefully I can do it. I don't think it's too bad. And again, this one comes out every year. So, I haven't seen this in a year. What year is it? Okay, so the implication is if two numbers A and B are even, then their sum A plus B is even. That's what we need to prove right now. So according to the rule above, we assume P and then prove, and then from that deduce Q. But first we have to identify what is P and what is Q here. So of course the statements are the things separated by the if and the then. So let's just highlight that. If two numbers A and B are even, that's the first part. Then, okay, this is going into 2 lines, so let me do it like this. Then there's some A plus B is even. Those are the 2 statements. The first one we will call P, as we always do. The second one we will call Q. Am I speaking gibberish for anybody just yet? So far, we okay. Just labeling statements, right? So now, assuming P is true, can we then show that Q must also follow from that? So assuming P is true, how do we write this mathematically now? If two numbers A and B are even, so to represent a number which is even, we can express A as 2 times, I'm just going to say J, where J is some, should I say whole numbers? Let's say integers here. So think about this form that I just wrote here. No matter what J is, A is going to be an even number. I'm just thinking for a second. Now, negative numbers can also be odd and even, right? You probably can. So yeah. So we'll use integers. Okay. Does the first step make sense to you guys? What I'm doing? It's just you got to kind of feel your way through these things a little bit. So we're saying A and B are even. We got to show a way mathematically to represent an even number, and this is the way to do that. Okay, 2 times J, where J is an integer. And think about it, any J you substitute here will give you something even. If J is 0, you'll get 0, which is even. J is 1, you'll get 2, which is even, and so on. So any J you plug into this gives you an even number. So A is always even. You still get even number. Because if you get something like negative 1, for example, this becomes negative 2, which is an even number. Even. Yeah, even. Yeah. So it's early in the morning. I don't know. Because it's early, I probably might make mistakes as well. So just watch what I'm doing. And not for your sake, for my sake as well. So B will represent it the same way. We'll call this 2 times, let's say K. We can't use the same letter, where K is an element of integers again. So same thing. P is an even number. So this right here is the bulk of the work. Once you've done this part, then we go to Q and see if we can prove that Q is true based on the assumptions we made in P. So Q says the sum A plus B must be even. Right, so this here we deduce from P. From Q, we deduce that the sum A plus B must be even. Right, so I'm just going to rewrite this A and B using the form we just introduced here. And I think we can see immediately that it's going to work out because this then becomes 2J plus 2K. Right, and we can factor 2 out because 2 is common here. This becomes 2J plus K. So this we deduce from Q. And now this answer that I get here, can you guys see that no matter what J and K is, this is going to be even because there's a 2 in front of it. So it doesn't matter what J and K is, this result here is always even. That's what we wanted to prove, right? So that's all you need to do here. So again, you guys see very little work here, but this question is almost guaranteed to come out every year in one form or another. They might change it and say, prove that if these two are odd, then the sum is odd, something like this, small variation. Is that even true? I wonder. I guess it must be. You guys want to try that as another exercise, maybe? Let's see if we have space here. Let me just write on another whiteboard. Sorry, is anyone still writing there? Give you guys a moment. Okay, all right. Take your time. It's early in the morning. We're not going to rush today. And sum is even. Is that always the case? Yeah. 3 and 5. It's even. So maybe we'll try that if two numbers are odd, then the sum is even. Yeah. Let's try that. I mean, if we can't prove it, it's okay, but we'll just give it a try. Yeah. No, you guys signed it here. Okay, so let me copy and paste this question onto the whiteboard. Where's the snipping? Here. Why is this so complicated? Yeah. No, that's not what I wanted. Yeah, I did the wrong thing. Okay, guys, you know what? I'm just going to be untidy with it. Doesn't matter. Change that even. Even. Okay, guys, let's try this one. If two numbers A and B are odd, then the sum A plus B must be even. Seems to be true. If we try a few examples, we'll see it seems to work. Okay, guys, take a few minutes. Try it very similarly to what we did in the first example. So now
oh, something beats in my mind. Wow, okay. Okay, oh my emotion and I think you finished. I'm still in. Changing focus from changing focus from my head. So yesterday, all night, from real, did you realize you get a lot after it and there's actually my purpose in life.
Okay, guys, anyone manage to get it? Huh? Anyone manage to get the example? Okay, so this one is not too difficult. It's not through and okay, let me just do it for you guys since it's early in the morning. So if two numbers A and B are odd, so that's our first statement. Two numbers A and B are odd. That's our P. Then the sum A plus B is even. That's our Q. So assuming P, we need to prove Q. So what does P tell us? It tells us A and B are odd. So how do I write that? Just like the same way we write an even number plus 1, because that makes it odd now. Because that's always odd. And again, J could be any integer, so we'll write that. And B is going to be the same thing here. 2k plus 1, where k is some integer. Okay, now the second part, you guys can probably see it fits quite easily. If this is the assumption made from P, then if I follow the instructions in Q, which tells me the sum A plus B is even, so it just tells me A plus B must be even. So can I now prove this A plus B is even? Yes, we can quite easily. I just substitute the A, which is wrote on the left. 2j plus 1, that's A. And the B is 2k plus 1. So this becomes 2j plus 2k plus 2. Just like before, now I can factor the 2 out because it's common. 2j plus k plus 1, which is always even, right? Because it's something multiplied by 2. Anything multiplied by 2, especially when these are sums of what's what I'm looking for? Integers. These are sums of integers, right? So there's no fractions or anything like that involved. Sums of integers times 2 will always be even. Okay for you guys? So again, just try to go over the first one and the second one. Anyone needs me to explain anything again here? Any questions? Okay. Okay, so that's just two examples for that. Okay, now we have to learn something called the converse and contrapositive. Again, now remember, because this whole section is based on implications, everything we do here is based on an implication. So converse and contrapositive both apply to implications and none of the other logical connectives. So the implication again is this one here. If P, then Q. And the converse of that, forget about this long story, it's too long to read. Converse of that is just switching the Q and P. That's all it is. The switching the places of Q and P. Okay, and the contrapositive at the bottom, again, is just taking the original, similar idea, switch the places of Q and P, but now we include a not before the Q and the P. We switch them and then you put a not in front of either one. Okay, and also we talk here about logical equivalence, which is an important concept. Logical equivalence means, for example, with the converse, if the first part here, the whole thing, if that is true, does it mean that this, if that is the case, we say they are logically equivalent, right? I'll say that again. If the first part, if the implication is true, and if that being true means that this is also true, then we say that the two are logically equivalent. But if their truth values are the same, they're logically equivalent. So in this case, the converse does not lead to something logically equivalent. So it's not logically equivalent. But the contrapositive is logically equivalent to the original. So that and that have the same truth value, completely equivalent. So if I work out that this implication is true, it means that that is automatically true. Again, if anyone is struggling to keep up with all the words, it's all summarized in the notes. So if maybe it's not too early at some point, whenever you guys have your best study mode, that's when you read the stuff. For some people are late night study people. Every night, yeah. So whatever works for you guys. Okay, and somehow this is just another thing to remember. And if and only if, which is not an implication, can be written as implication. So if we have an if and only if, which is represented by a double-sided arrow, which you guys may remember, it is completely equivalent to rewriting it in this form here as two implications separated by an and. So again, just telling us that these are logically equivalent. So if you don't like working with one, you can work with the other. And unfortunately, lots of words to remember here. The words necessary and sufficient are words we have to remember as well. But again, these are summarized at the bottom here. Okay, so let me give you guys a moment if you're still writing. Okay, so as I was saying, necessary and sufficient are words we have to remember. So if you say P is necessary for Q, it means it's an implication of the form if Q then P. That's the first line above. If P is sufficient for Q, it means if P then Q. So again, there's nothing much more than just words to remember here. And the words tell us how to structure the implication. And if something is necessary and sufficient, then it's a double-sided arrow, which means it's an if and only if that we see at the bottom there. And if and only if can be rewritten as implications as well, which we just saw above. Okay. So we have a task at the bottom here. What's this telling us to do? The following is if and only if. Okay. So do you guys want to try this or do you want me to do it? Okay, so here when they say the box above, they're talking about the box which tells us that. I'll just rewrite the rule here. P, Q, the implication can be rewritten as or is logically equivalent to. What was the order? The order doesn't matter, but let's just be consistent. First, we have P, Q, and Q, P. So rewrite the first one as the second one, which is completely logically equivalent. And we are given two statements here to try with. Oh, sorry, there's a double set arrow at the bottom. Yeah. Okay, thank you. Since everyone is looking a little bit tired today, let me at least start by stating the statements here for you guys. I will. In fact, guys, for the answer, I don't have to write anything. I'm just going to say it out loud. So you guys, I'll give you guys a minute if you want to try it. You're gonna take a 1-minute power nap as well. You can do that. It's up to you. Okay, so guys, let's look at this one. And this is a good one if you want to get into politics and stuff like that, because it shows you how to reword a very simple sentence in a very complicated way. And so this one here, the implication, not the implication, sorry, the biconditional is telling us, I watch a movie if and only if it rains. Firstly, that's a weird thing to say. But anyway, that's what they're saying here, right? Now, what we're saying is this is completely equivalent to saying it like this, which is P is up here. If it rains, then I will watch a movie, and it rain if wait, we already messed it up. P is I will watch a movie. So if I watch a movie, then it rains, and If it rains, then I will watch him. Right? Okay. So that's a weird way to say a very simple thing, but it's just showing us that we can say that, and technically it means the same thing. I feel like our guys in Parliament know all this stuff here, though. If you ever watch those, you guys are too young to watch all those things. Every year I teach this module, my jokes get further and further away from you guys. I spoke about Johnny Bravo once, and people asked me, who's that? Hey guys, in this day and age, you can't talk about Johnny Bravo. He's like a womanizer. Okay. So now more stuff to learn, more stuff to memorize. Universal and existential quantifiers. So this learning unit has a lot of new stuff to memorize, fortunately, and I can't help you guys with that. We have to just memorize them. Okay. So it's like a way of writing mathematical things. Sometimes you guys see me writing things like X is an element of real numbers. It's just kind of in the same language, just different symbols to represent things like this. So the first one we look at is called the existential quantifier, which is represented by an upside down E, sort of like a capital upside down E, which is helpful to remember the word existential because it looks like an E. And what it tells us is that they exist. That's what it's telling us. They exist. All right, so how we will read this thing at the bottom here is there exists an X where X is less than 0. All it's telling us. So this here, there exists an X, and that's the condition where X is less than 0. Just need to know. Yeah, that's it. That's it. I mean, we could write that in words, but yes. I said, you mean what this means? It means that it exists. Yeah, again, I'm just reading this. It's kind of like another language with symbols. So what the symbols are telling us is that there exists an X where X is less than 0. That's all. Yeah. Okay, so the second one is called the universal quantifier, which has the symbol of like an upside down A. And this is read for all or for every. Let's highlight that. It's easier to remember the for all because it looks like an A, upside down A. So it goes with the word all, for all. Again, whatever you guys' memory methods are, just use that. This is just a memory thing. So the way we read this at the bottom here is, let's bring this up a little bit, zoom in. For every X, or you can say for every or for every X, there is an X greater than or equal to 0. Again, just a way to read this. For every X, there is an X greater than or equal to 0. Or alternatively, if you wanted to, we could just say for every X, X is greater than or equal to 0. That's also another way of saying that. Maybe a better way of saying it is the second way, but either way is fine. For every X, X is greater than or equal to 0. And you can see these things kind of put restrictions on numbers. So sometimes you'll see these things next to equations where this is now asserting that x is always positive. Right? Things like that. Okay, and let's try to do one more before I think I'll give you guys an early break today. Might be necessary. Okay, so let's just do one more before the break. See, that's how I get you guys to pay attention. Now everyone is here. Okay. Okay, do you guys think, based on the first two things we just read, can you guys try to read the statement at the bottom here? Just remember what means what. And here we can pull in words using English, doesn't really matter, but something like, for every x there exists a y where y is less than x. So it's not so bad, right? Just like 2 words in a new language that we learned, that's about it. And is the statement true or false is another thing. Does it seem like a true statement? Every x there exists a y. I guess it depends on which numbers we're talking about. Let's say we're talking about whole numbers. Then is this true for whole numbers? Because this is saying you can always find another number which is less than the previous number. Yeah. So if we go to 0, can you find a number less than that in whole numbers? With whole numbers, you can't, right? Because that ends at 0. So again, it depends on the domain we're talking about. If you're talking about the domain of whole numbers, this is false. If you're talking about integers, then this is true. In integers, you can always find a number less than the one you're looking at. Again, that is on the video. So if anyone lost it, you can just go back and listen to that again, try and make sense of it. Or you can ask me. We have a little break now. If anyone wants to stay behind and do work, which I doubt, you can stay here and ask me questions. Okay. All right, guys, let's take, I'll give you 20 minutes today. You look like you need it. Yep. Let me just stop the video and be with you. Stop it.